Hey, welcome to the Electronics channel. In this video, I'm going to be talking about voltage sources and current sources and the equivalency between the two of them. To start off with a voltage source, I'm just going to be really brief when I describe these two different types of sources. Voltage sources, the symbol that we use to model them in a circuit, typically looks something like that, although sometimes could also be like that. That's usually to indicate that it's a battery and then there's two cells of the battery. And voltage sources, of course, are devices that will provide a constant voltage regardless of what kind of load is connected to them here. And current sources are devices that provide a constant current regardless of what load is connected to them. And the symbol that we use for current sources looks something like that. Examples of voltage sources, there's all sorts of examples. It could be the wall outlet. That would be an AC source, of course. And batteries are a really good example of them as well. Current sources actually occur quite frequently in the real world as well. We're just not as familiar with them. They occur in all sorts of electronics components, as well as probably one of the best examples would be in LED lights. The way that you control the brightness of an LED is by varying the current through them. So there's often constant current sources or variable current sources that are used for controlling LEDs. And action. So these two sources here, the voltage source and the current source, are both ideal sources. They only provide a voltage or a current, and there's nothing else to consider. To take one giant step towards modeling these sources as real-world sources, we can add some internal resistance to them. So on the voltage source, we'd add the internal resistance in series with the voltage. And on the current source, we'd add that internal resistance in parallel with the current. Now on the voltage source side, that RS sets an upper limit for the current. Now you can imagine as the load gets bigger and bigger, so it's drawing more and more current, there'll be more voltage drop across RS because there's more current going through RS. So there's some limit to how much your output voltage that you can have. So that V out is actually going to be equal to Vs minus whatever current's going through RS times RS. So if we ended up with a short here, you mean obviously V out is going to be 0 because all of the voltage drop from the source is across that internal RS. And you can see this in a real world example. If you take a little battery and you connect a big resistor to it, and measure the voltage at the terminal of the battery, it's pretty much the nominal voltage of the battery. Whereas if you take a really small resistance across the battery, and only do this with like a AA battery so you don't have too much current coming out, with a small resistance across the AA battery, you'll see, and you measure the voltage at the terminals, it's much less than the nominal voltage of the battery. Over here on the current source side, the RS sets an upper limit to V out. And if we look at an internal current here through RS, just call that IRS, V out is equal to IRS, so the current going through RS times the value of that internal resistance. And that IRS is equal to whatever's coming from the source minus whatever's going to the load times RS. So there's my I out right there. And in an open circuit, that I out will be 0. So my V out will simply be, well, let's look, open circuit. V out. If it's open circuit, I out is 0, so V out is just going to be IS times RS. But as that load gets bigger and bigger, so as if you connect something here and the current, and you actually have some I out current, as that current gets bigger and bigger, then V out's going to get smaller and smaller. So with a load of any kind, V out will always be less than that IS times RS. So you can see that RS sets the limit for what your V out voltage can be. Now we're going to look at the equivalency between voltage sources and current sources. And to do that, we're going to use a principle that you'll often use in circuit analysis, and that's where you look at the circuit from the point of view of a piece of the circuit. And so in this particular example, we're going to look at this overall circuit from the point of view of this load. And this load doesn't really care what the source is. It just knows that when it's plugged in, it's going to have a certain voltage across it and a certain amount of current through it. So in principle then, we could have either a voltage source as this source or a current source as the source. I just realized I have this current source going the wrong way. So there we go. Okay, now let's look at a couple of extreme cases just to get an idea of how these two can be equivalent. To start off with, let's look at the case of there being a short here. So our load is a short. Here our load is a short. So then if we have a short, then what's going through here will be IS. And what's going through here on the voltage source is Vs over Rs. So for these two to be equivalent in the short circuit case, Vs over Rs should be equal to Is. And now let's look at the other extreme, where we have those two sources. Can't forget that internal resistance. So Vs and Rs, and over here we have the current source and Rs. So if we look at the case of this being an open circuit, and we want the voltages here to be the same, the voltage on this one, the output voltage on the open circuit is simply equal to Vs. And in order for the output voltage of the current source to be equal to Vs, then Vs must be equal to Is times Rs. So these two equations for the open circuit case and the closed circuit case are actually the same equations, they're just rearranged in slightly different ways. So what this is telling us is that there is an equivalence between the voltage source and the current source. As long as that internal resistance is the same for the two, Is is equal to Vs over Rs, or Vs is equal to Is over Rs. So I can switch back and forth between these two. So if I'm given this in my circuit, and this is connected to some kind of load, if it makes it easier for me to solve the equation or to solve the circuit, to analyze the circuit, I can convert that into a current source where that current source is equal to Vs over Rs. And in a future video, we'll look at some examples of how we do this. But the general idea is you can have a voltage source or you can have a current source, and you can convert between the two depending on which one is going to make your analysis easier. Now I want to confirm this equivalency where with a case where the load is not an open circuit and it's not a short circuit. So in this case, we'll have the load resistor to be a 1 kilo ohm resistor. And what we want to figure out is what is the voltage across this load resistor and what is the current through it. And these are the two equivalent circuits. So here's a 100 volt source, 10 ohm internal resistance, and over here the current source is 100 volts over 10 ohms, doing that equivalency calculation to give me 10 amps with the 10 ohm resistor in parallel. So over here, the load current is simply going to be 100 volts over 1010 ohms. And that equals 0.099 amps. And since we have 0.099 amps going through both of the resistors, specifically the load resistor, the voltage across the load resistor will be 0.099 amps times 1000 ohms. And that equals 99 volts. So we have 99 volts across that load. Now with this equivalent current source circuit, what we have, we've got the load is again 1000 ohms. The voltage, let me do that in green so I can match the color over here. The voltage across the load will be 10 amps times, 10 amps is going through both of those resistors, so the parallel equivalent of those two resistors. So 10 ohms in parallel with 1 kilo ohm. I won't do that actually calculation because I'm sure you know how to do parallel resistors. And that works out to 99 volts. Oh, and what do you know? The load voltage is 99 volts for the current source and 99 volts for the equivalent voltage source. Now the current through the load will be 99 volts over the resistance of that resistor, which is 1000 ohms, and that works out to 0.099 amps. And again, matches what we had with the current source circuit. So hopefully that shows you how current sources over here. That shows you how current sources are equivalent to voltage sources and how to convert between the two different ones to give you the equivalent circuit. Thanks for watching. And what am I going to do? See you in the next video. Bye.